Greetings of the day. Welcome to the course on Operations Research Technique. In the last lecture, we have studied various aspects of linear programming. We have studied how to formulate the equivalent linear program in the form of mathematical equations from given wording data. Now, once we formulate the mathematical model for given data, then it is necessary to solve it for optimization. We have seen optimization may be maximization or minimization of the related objective function. Now, when we did the task of formulation of the problem mathematical model from given data, further step includes finding solution of those decision variables which we have assumed in the form of let x1 and x2 be the decision variable corresponding to given objective function. For finding solution to given LPP, two methods are available. One is graphical method, other is analytical method, also called as big M method or simplex method. First, we will study graphical method for finding solution to given linear programming problem. Now, when I am saying graphical method, we know the nature of simple graph. It is 2D, means you are having two axes, horizontal axis x and vertical axis y, or we can call it as axis x, axis y, or axis x1, axis x2, as the case may be. Means graphical solution is limited to only two variable problem. That is, if in a problem only two decision variables are there, then only we can go for graphical solution of the problem. But in reality, we know that there are so many cases wherein we are facing multiple variable problem. In that case, it is impossible to find solution of those problems with the help of graphical solution. In that case, we have to follow analytical method. So now we will go into details of what is graphical solution, how we should proceed, and what are the related requirements for graphical solution. So let us move ahead for finding graphical solution to given linear programming problem. So as mentioned here, you can see here for LP problems, as I have already explained, that have only, this is very important, that has only two variables. That is two decision variables. We have assumed let x1 and x2 be the number of decision variables for objective function, whatever quantity we are producing. For LP problems that have only two variables, it is possible that entire set of feasible solution can be displayed graphically by plotting linear constraints on graph paper. So we will be drawing linear constraints, that is, we are having equation of line and we will be converting those equations of the line into coordinates of the line. We will plot those points on the graph paper, we will plot the line, and we will find solution for the given problem. That is methodology. The technique used to identify the optimal solution is called graphical solution method or approach or technique. Another name for this method is approach or technique for an LP problem. But essential condition is this, that is, it is only for if problem is having only two variables. If problem is having only two variables. For others, more than two variables, we cannot use this particular method. So now we will go ahead. We will see graphical solution. Basically, two methods are available for our rescue in graphical solution. In that, first method is extreme point solution method, which we will be following. Other is similar to the same but isoprofit line method. We will be studying extreme point solution method of finding graphical solution to given linear programming problem. Now, what are the requirements of this process method that we will see? In this method, the coordinates of all corner, the word all corner or extreme points of the feasible region, this is very important, feasible region are determined. First we will be determined the coordinates, means x1 coordinate and x2 coordinate for the given line are determined, and then value of the objective function at each of these points is computed. Once we get feasible region, so we will be evaluating the value of objective function for each of the identified points. The coordinates of an extreme point where the optimal may be maximum or minimum value of the objective function is found represents solution of the LP problem. Various steps are mentioned which are given over here. The steps are: develop an linear program model. Students, we have seen many varieties of the problem wherein we have practiced how to develop the linear model from the given solution. We have seen in earlier lectures methodology for formulation of the model from the given data. That part is over. Step 2 is plot constraints on graph paper. Plot constraints on graph paper and decide the feasible region. After drawing these constraints on the graph paper in the form of straight line, we have to decide the feasible region. We have to decide the feasible region from the identified constraints, and then examine extreme points of this feasible solution space to find the optimal solution. So once we find the feasible region, by considering all constraints of the problem to achieve the desired objective function, we will be getting some feasible corner points. For each of the feasible corner point, we will be identifying its objective function value in the form of maximization, and then amongst those values we will select the value which satisfies the given objective function, meaning whether it is maximize or minimize profit, that will be dealt. To go ahead, all of us are familiar with this simple graph which represents 2D format. So here we are having simple graph paper wherein we can see different boxes are there, and on this graph paper we can plot different lines. So suppose I am assuming I am having two variables x1 and x2. For those two variables, how I can proceed is I will explain this through simple concept. Now we know whenever we plot any lines on the graph, then we identify first two axes. So here I did that job. Now this is the first quadrant. This graph can be divided into four quadrants. Quadrant 1, first, 2, second, third, fourth. So we are working in the first quadrant wherein we are having values of x1 axis, values on x1 axis as positive value, values on x2 axis are positive value. There may be situation where we are required to plot minus values of x1 and minus values of x2 as per condition given for the constraint of the line. Now this is prerequisite for finding graphical solution to a given problem, and based on the logical constraints, we will be finding first coordinates of the points. After finding coordinates of the points for the given constraint equation of that situation, a line will be drawn, and based on positions of different lines with respect to x1 and x2 axis, we will identify feasible region where our solution exists. So definitely while solving problem we have to assume some scale in the form of that on y-axis. Suppose we have to mention on x1 axis what will be the scale, that is 1 centimeter is equal to suppose 1 unit as the case may be, and on y-axis x2 axis again 1 centimeter is equal to suppose 1 unit. If it is same on both axes, I can write simply scale on both x1 and x2 axis as 1 centimeter is equal to 1 unit. The meaning of the scale is that if I am plotting 3 centimeters, it will represent 3 units, provided if I take 1 centimeter is equal to 1 unit, or if I take 1 centimeter is equal to 1 unit, 5 unit, 1 centimeter equal to 5 unit. So in that case, the distance equal to 1 centimeter will represent 5 units of products. If it is 2 centimeter, it will be proportionally representing 10 units of product. For 3, it will be 3 centimeters, it will be representing 15 units of product. If it is scale is 1 centimeter equal to 5 units. So it is how to decide what scale is to be selected. It is the number digits which you get from the equation of straight line. If you get x1, x2 coordinate to a very large value, and we know limitation of graph paper, to accommodate that larger values of x1 and x2 coordinates, we know that we have to take bigger scale, that is 1 centimeter is equal to larger value, and then only we can find those, we can plot those values on the graph paper. So this graph paper is prerequisite for finding graphical solution to a problem where only 2 variables exist. I am again stressing, graphical solution holds good for a problem wherein you are having only 2 variables, x1 and x2. The moment you exceed 2 variables, if your problem is having 3 variables or more than 3 variables, this method is not suitable, not applicable, or you cannot find solution for more than 2 variable problem with the help of graphical solution. Students, remember, in real life you will hardly have a problem wherein you will come across 2 variable problem. In real life there will be multiple decision variables in day-to-day life, and for that you have to use analytical method only. Nowadays modern softwares are available at your rescue to overcome these lengthy calculations, iterative calculations of the mathematical model. But this particular aspect of finding solution to given linear programming problem by graphical method, which is suitable for 2 variable problem, gives us idea, gives us insight to the solution of the problem, how by changing the phases, how by changing the state of variables at each iterative step our solution continuously improves in a progression. One beauty of linear programming is that it gives you improved solution after every step. Remember, we will be starting from scratch only. Scratch means whatever decision variables we are assuming, those decision variables are equivalent, taken equivalent or considered equal to 0, and then only after that we'll go ahead for improvisation of the given problem. So this is the theme. Now let us go for finding solution to the problem. So here this is the problem wherein now what I did is, we have practiced so many problems for linear programming formulation. So we are taking advantage that we know how the problem is formulated, and if you recall that problem of panes with models alpha and beta pane, which is the first problem in our discussion, There we have formulated this mathematical model which is displayed on the board with the condition given in the problem, and we could arrive after finding this formulation for the given problem in the form of objective function. So in that particular case, the objective function was maximize total profit subjected to 5x1 plus 6x2 and subjected to constraints. We know that first constraint was related with resource R1, second constraint was related with resource R2, that we know very well, and last is non-negativity condition. Now what we are supposed to do, we want to find the values of, we want to determine the values of x1 and values of x2 from logic of graphical solution. That is our task. So first thing in the steps, if you recall, we have mentioned the first step in graphical solution, in finding solution to a graphical solution, was formulate linear program from the given data. So we did that. We have formulated linear program from the given data. This is linear program. Now at the end of the linear program formulation, we are interested in finding the real values of this x1 and x2. That is our task, and for that we will be using graphical method to finding the for finding solution. So here we go in this way. So now what is first required thing is x1 plus x2 is equal to 5 or less than equal to 5, means the value of 5 at the most for addition of x1 and x2 maximum can be 5 or less than equal to 5. That condition you have to remember. So I can plot this line on the graph paper, x1 plus x2 less than equal to 5. I can definitely plot this line on the graph paper provided I find two coordinates. We know that for drawing any line, any straight line, we need two coordinates. We need two coordinates, 2 points, say point A, point B, and for that point we need x1 and x2 coordinate, or if I say x and y coordinate. Now for this case of first x1 plus x2 less than equal to 5, for finding two coordinates, how we go here, listen carefully. Here put x2 equal to 0. If you put x2 equal to 0, you get x1 equal to, if you put x2 equal to 0, you get x1 equal to 5. So first coordinate is 5, 0. How you get it? Put x2 equal to 0. If you put x2 equal to 0, you get x1 equal to 5. Similarly, other coordinate, for putting other coordinate, put x1 equal to 0. Now reverse, put x1 equal to 0. If you put x1 equal to 0, you get x2 equal to 5. Means I can draw now this line x1 plus x2 less than equal to 5 with coordinates 5, 0, 0, 5 on graph paper, and I can draw this straight line. Similarly, we'll see now how to get coordinate for second line. So going in the same fashion, listen here, put x2 equal to 0. If I put x2 equal to 0, 2x2 is 0. So therefore 3x1 is equal to 12, 3x1 is equal to 12 and x1 is equal to 4. So what we did? We put x2 is equal to 0, and by putting x2 equal to 0 we get 3x1 is equal to 12 and therefore x1 is equal to 4. So we get first coordinate, first point for this line as 4, 0. In the similar fashion, for getting other coordinate, put x1 equal to 0. If you put here x1 equal to 0, getting it? If you put x1 equal to 0, 3x1 is equal to 0. So your equation becomes 2x2 equal to 12. So x2 is equal to 6. So your point becomes 0, 6. I think method is clear now. How to, it is very simple, that for getting other coordinate, for getting say second coordinate, value of second coordinate, put first coordinate 0 and vice versa. Now our task is to plot this line on a graph paper. Our task is to plot this line in the graph paper, and we know now maximum distance on graph paper which I need is 6. Before some time I have used that you have to take the scale. If this would have been 600, 800, I cannot use the scale 1:1 because I don't have 800 divisions on the graph paper. So there I have to take bigger scale. 1 centimeter is equal to, say in that case, 50 units, like that. So here our further task is to now plot these lines on the graph paper. So how we should do that? So what I am doing, I am leaving 2 centimeters apart from left edge. So this is one axis. Similarly, same distance, I am moving on right side. So x-axis I will label as x1, y-axis I will be labeling as x2. These are my decision variables. And now scale I can take 1:1 also or 1:2 also. Scale will take same scale on both axes. On x1 and x2 both being same, say we write here to understand 1 centimeter is equal to, suppose, 2 units. Means here what we'll do, this is 1, this is 2, this is 3, this is 4, this is 5, 6, again it is 7. If the scale would have been 1:1, I would have drawn 1 over here after 1 centimeter. Since I have taken bigger scale, I am using 1 centimeter equal to it is wrong, 2 centimeter, it should be 2 centimeter equal to 1 unit. 2 centimeter equal to 1 unit. Two centimeter equal to 1 unit. Next 2 centimeter equal to 1 unit. So scale is like this. So I am enlarging this space. If it is more value, we have to reduce the scale, like 1 centimeter equal to 50 units, like that. So for clear figure, being first problem, I have taken 2 centimeter equal to 1 unit. Same I will be plotting on y-axis or x2 axis. 1, 2, 3, 4, 5, 6, 7. That's all. Well, if you are having bigger graph, you can also enlarge this, that 3 centimeter is equal to 1 unit. Choice is yours. Now question is how to plot first line, x1 plus x2 less than equal to 5. This is very important now. First coordinate is 5, 0. So 5, 0 is this coordinate. 5 x1, 5 x1, 0 x2, 5, 0, and 0, 5. 0, 5 is this coordinate. Hope it is clear. What you have to do is you have to simply join. You have to simply join these 2 points. and I am labeling now. Make it practice. So these lines represent x1 plus x2 less than equal to 5. I did my job. Now one important point which is to be understood. If you put here your palm, it reflects value of x1 less than equal to 5. So maximum value which x1 can attain is 5, which is ranging from 1 to 5. Similarly, if you put your palm over x1, x2 less than equal to 5. So maximum value of x2 is 5, rests are less than equal to 5. To implicate this sign, what I am doing is I am plotting the zone. See here now, drawing this arrow indicates all values of this line holds good for all values of x1 less than 5, maximum 5 and less than 5. Similarly, this line holds good for all values of x2, maximum 5, remaining less than 5. So that is how you have to treat this particular less than equal to sign. Now second line will plot, which is 4 0. So 4 0 is this point, 4 0 is this point, clear? 4 on x1 axis, 0 on x2 axis, and 6 0 is this point, 0 6 on y axis. Again do the same process. So what we'll do, we'll be joining these lines, and here we'll write the equation for this line as 3x1 plus 2x2 less than equal to 12. So in the similar fashion, now here remember, if I put like this, 3x1 less than equal to 12 means x1 maximum can take value of 4. So again I will be drawing this arrow like this. Similarly, 2x2 maximum value is 6. So I will be lying. So whenever you are plotting any line on the graph paper, remember you have to identify the related area. You have to identify the related area which will cover that particular line. Now these are the coordinates of this graph, x2 axis, x1 axis, and you can see now, actually we know in mathematics these two equations are referred as simultaneous equation. Even on your calculators, programmable or simple calculator, you can find values of x1 and x2 which will satisfy these conditions, being simultaneous equation. But we are not supposed to find in OR the value of these particular two equations in a simultaneous equation form method. We have to find by graphical. Now since these two constraints are given and objective function is to achieve this total profit, remember this total profit can be achieved, this is a very important aspect, this total profit can only be achieved if you simultaneously, I am using the word, you simultaneously at the same time satisfy these two constraints. First constraint we know it is related to R1 in that pain, alpha and beta pain problem. Second constraint was related to resource R2. To achieve that objective function Z, that is maximize profit, total profit Z equal to 5x1 plus 6x2 is possible only if you simultaneously follow these two constraint equation. Now here we have plotted, we have identified the regions of these two lines which are common with x1 and x2 axis. See, this point of intersection of these two axes is definitely, we know that it is 0 0. if I consider, I will be first plotting and I will be erasing. If I consider this particular region which I have marked with red pen. So this particular region is satisfied by this line. Very important. This particular region is satisfied by this line, but not satisfied by this line, because this line says area below this. Similarly, this region is satisfied by this line, not by this line. So we have seen two cases wherein in this case this line obeys, this line does not obey. In this case red color line obeys, saffron color line does not obey. We have to find the region, common region, which both line obeys. So if you look, to figure, I have erased the area which is not common to both the line. Now if you carefully identify, you will get this as, I am marking it with some hatching. This marked region as feasible region, this marked region as feasible region for both the lines. See here, I have not considered this region, I have only considered the region which is common. So again, that is region from this line to this line, this line to this line, this line to this line, and from top to this origin line. Now I will try to represent this with points. This feasible region corner points as A, B, C, and this is 4 point as I will say it as D. So I know the coordinate of point A, 0, 0. Coordinates for point B are, this is point B, this is point B. The coordinate for point B, x1 coordinate is 0, x2 coordinate is 5. Now one thing you have to keep in mind, the accuracy of the solution in graphical method will depend on how precisely you draw straight lines on the graph paper. Your precision will give you accurate answer. If you are drawing in a haphazard way, your answer will deviate from its true value. That you have to keep in mind. This is C coordinate. Now here I can find for this C coordinate, it will be lying somewhere here, because I have done some the line, since I have drawn with the help of my hand without using scale, is now straight. So it is approximately reflecting 2, and on this axis it is 3. If you draw it correctly, you will get the points 2 and 3. And for D, the coordinates are 4 and 0. 4, 0. For D, the coordinates are 4, 0. D 4, 0. Now, in graphical solution, what we got is very important. From the given constraint, we got feasible region. which takes care of this particular objective function. This feasible region is now confined by the segments AB, BC, CD and DA. It is very sure now that for this two variable problem which we have formulated from given data, our solution now lies only in the confined region ABCD, that's final. Therefore, I have written here feasible region, means my answer is now in this hatch region indicated by ABCD. It can be any point, my answer point can be any point for x1 and x2 in this region ABCD. It may be any point, this point, this point, this point, this point, this point, this point, like that. But as per mathematical corollary, we know that simple principle: if this is the segment, and if endpoints of the segments are satisfying the condition, remaining in between points automatically satisfy the conditions. So to represent entire zone covered by the segment A, B, C, D, now on the basis of mathematical corollary, we have to only consider the extreme points, and therefore the name of this particular method is extreme point method for finding solution to a graphical problem. So extreme points of this particular feasible region are identified now, which are A, B, C, D. So here what I did is I have prepared a table which represent feasible corner points. So as you can see here, our feasible corner points are A, other B, getting it or not, then next C and next D. Remember, depending upon the case in the given problem, you may have sometime only two feasible points, sometime three feasible points, sometime more than 4 feasible points also, that is possible. But you have to be very careful, you have to identify feasible corner points. That we did. And now what we will write? We will write the values of x1 and x2 coordinates for those feasible points which are representing our solution zone. So for point A, we have written 0, 0, means x1 is 0, x2 is 0. First we will do this task of finding the points from the feasible region. For B, we know always we write first x1 coordinate and then x2 coordinate. So for B it is 0 and 5. It is 0 and 5. For C, this is point C. For C it is 2 and 3. If you draw it precisely, you will get the point 2 and 3. Here we can find this equivalent to 2. This point, actually intersection is here, but you can see line is somewhat, it has gone upward. So if you draw it exactly, it will pass through 2 and 3. And for D, it is 4, 0. So students, what we did till now is we have drawn mathematical straight lines on a graph paper from given constraint by finding its coordinates. Then we have drawn straight lines. After drawing straight line, we have marked area which is which these lines cover, and based on that we have omitted this area, and we have identified the feasible region which simultaneously, again I am using the word, which simultaneously satisfy these conditions, to get desired objective function, Now our task is only to find the values, and here no objective function. Now here I will erase this I have written for practice. So if it is maximized, I will only write maximize, so there is no need for this minimize, so I will erase this. My task is only to maximize, so I am writing for maximize, and I know it is 5x1 plus 6x2. Simply what you have to do? You have to multiply. x1 value is 0, so 5 into 0 plus 6 into 0 is 0. Put the values of x1 and x2 in the equation. Simple. If I put again here 0 into 5 is 0 plus 6x2. So it will be how much? 30, equal to 30. For third case, what I will get? 5x1 is, it is 10 plus how much? 15. It is 25. Then last is 10x1, this 5x1 into 4 is 20 plus 0, it is equal to 20. So once you calculate these values, based on your values, on the basis of whatever you get in, after making your scale as a responsible unit for that particular dimension, here the unit was taken 2 centimeter equal to 1 unit. 2 centimeter equal to 1 unit. So as at 2 centimeter we have plotted 1. Here we have plotted 2, like that, and accordingly we have plotted these points to get exaggerated view of the plot. Similarly, in real cases, once you go for this concept of finding the values from the given constraints and identifying the feasible corner points from the solution, further you have to attempt your maximum value, and maximum value can only be obtained by seeing whether that particular constraint is being satisfied or not. As mentioned here, and as practice, after developing this particular model, plot the constraints and examine the extreme corner points from the feasible solution. So once you are having the set of various corner points, then your task is to conclude how you are getting the solution from the points under consideration. And once you did that with the help of graph, which again I will be recalling, here on this graph you have to write scale, here you have to write scale, here you have to write scale, then you have to plot these axes as per the requirement. Label and further find the values. So with this prerequisite, in next lecture, in coming lecture, we will again go through various aspects of this first problem with, if we have selected the scale in today's lecture like 2 centimeter representing 1 unit, what will happen if we select the scale of 1 to 1, and accordingly how we should go and conclude with final problem. That aspect we will be studying with more varieties of problem pertaining to 2 variable problem, which will take care of maximization type of objective function, minimization type of objective function, and mixed constraint all less than equal to, constraint all greater than equal to, or constraints less than equal to, greater than equal to, equal to. So depending on the situation, if you are having all equal to constraint, definitely for 2 variable problem we can find solution. If we are having all less than equals to constraint, for 2 variable problem we can find solution, and vice versa. So in next lecture we will go with details of this particular thing for various problems. So here today we will end our today's lecture, and from next lecture we will see the current problem with additional more number of problems. So till practice whatever I have explained till date. See you in next lecture.